This video is going to look at inverses of functions. So the definition of an inverse of a function is it is a reflection over the line y equals x. So you think about what the line y equals x is. It is at that 45-degree angle. So when we are finding an inverse of something, we're just reflecting it over that. Another thing that you might notice is that basically what we're doing when we reflect is we're switching x and y. So one thing you're going to see a lot in this video is I'm going to be talking about flipping x and y, or switching if you like that word better. You can do inverses of functions algebraically, which is the best way, right? And graphically, by reflecting it over that line. Or you can also think about it in terms of tables by flipping x and y. And that's going to invert it. And you can, if you think about it, you're switching the x and the y. You're inverting the function. We'll look at some examples of inverses of each other in some of the following slides. That's just to get the definition out of the way. So here we have a graph of a just generic function. And if we want to find the inverse of it, remember we're going to be looking for a reflection over that line y equals x. You can kind of feel it out with the graph if you want, but one thing that I find makes it easier is to look at it in terms of a table. And I'm going to make a table of all the points. So I have the point negative 6, 4. I have the point negative 1, 3. And I have the point 4, 6. I have the point 7, negative 2. And I have the point 5, negative 6. So that's my function as it stands right now. But if we are going to find the inverse of this function, we are going to switch x and y. So for the first point, that's going to be the point 4, negative 6 now. So I'm gonna graph that one. 4, negative 6. There it is down there. You can see that this is a reflection over that line. You can see how it's equidistant away, sort of, if my line were really awesome. And so by doing it with a table, that actually made that part a little bit easier. So let's continue our inverse. We had the point negative 1, 3. Now it's going to be the point 3, negative 1. We had the point 4, 6. So it's going to be 6, 4. We had the point 7, negative 2, which flips to be negative 2, 7. We had the point 5, negative 6, which now becomes negative 6, 5. So let's go ahead and graph the rest of these points too. 3, negative 1, and then 6, 4, and negative 2, 7, and negative 6, 5. I'm going to connect my points so we can kind of see our reflection. Kind of cool. If you were to flip that blue graph over that line, over that red line, y equals x, you can see that they would match up. Now, yeah, my drawing is not perfect, but that flipping of x and y enables us to see what the inverse would actually be. So here you saw an example of both a graphic inverse as well as doing the inverse with a table. So now we're going to look at some algebraic ways to find the inverse. So here we have the function y equals x plus 7. That's just a line. It has a y-intercept at 7. And we want to find its reflection over the line y equals x. We just want to find its inverse. Now in this case I'm going to do it algebraically. And to do this I'm going to flip x and y. That means I'm now going to have x equals y plus 7. I just switched positions for them. And then, if we're going to do this algebraically, we want to solve for y. That's how we like our functions in algebra. So if I solve for y, that means gets y by itself. So I'm going to subtract 7 from both sides. I'm going to end up with x minus 7 equals y, or y equals x minus 7. And that's it. That's my inverse. One thing that you'll probably want to remember is that generally we use a little negative 1 power there with the y, and that represents the inverse. What this says is that this is an inverse function of something. So the inverse of y equals x plus 7 is y to the negative 1 equals x minus 7, or y inverse equals x minus 7. So let's think about this as a graph, because this is the easy one to graph. It's going to be a reflection over that line, y equals x. And normally, our first graph would have been shifted up 7, and then it would have followed that same slope. Now our inverse graph has been shifted down 7, and it's going to follow that same slope. Kind of cool. If you were to fold them on top of each other, they would match up. It would be that reflection over that line. So for the function y equals x plus 2 squared minus 1, this one's a little bit trickier to actually find the inverse of algebraically. We're going to start out, though, by flipping x and y, just like before. So then we would have x equals y plus 2 squared minus 1. Now remember, we need to solve for y. We want to get y by itself. So we need to isolate y. Well, the first thing I see that's just hanging out over there that has nothing to do with anything is that 1. So I'm going to add 1 to both sides. So now I have x plus 1 equals y plus 2 all squared. Now the next thing I need to do is I need to get rid of those parentheses, and that squared is keeping me from being able to do that. So I'm going to take the square root of both sides. So now I have the square root of x plus 1 equals y plus 2. I almost have y by itself. There's only one more thing to do. Got to move that 2. So I'm going to end up with the square root of x plus 1 minus 2 equals y. If we want to think about that all fancy like, we would say the inverse is the square root of x plus 1 minus 2. Now before you think you're actually done, because you're not, let's think about the graph that we have going on here. We originally had this parabola, and it had been shifted over 2, and it had been shifted down 1, and then it followed its basic parabola stuff. We want to reflect it over the line y equals x. Well, now let's just look at the inverse, and graph the inverse based on what you know about power functions. You can even choose a whole nother color for this. If I were going to graph this guy, I would say, okay, it's been shifted to the left 1, it's been shifted down 2, and then it's a square root graph. So, ooh, that looks like that. But wait a minute. I took a parabola and I made it into something that's just half a graph. That's not actually the inverse of that parabola. I need the second half of the graph. I need this part right here, right? So I can see that, oh, it actually is a reflection. So you have to think, what do we need to get that extra part? Well, if we looked at just the bottom part, I wish I could cover, anyways, if we looked at just the bottom part that I sketched in green, that is the exact same function I graphed, but just reflected. So one thing that we want to be careful of is that when you are finding the inverse of a parabola or another even power function, you are going to need to include not just the positive case, but the negative as well. So that's sort of our little warning on this one. You need a plus or minus for x squared to the square root of x. So now we actually have the inverse, because the inverse includes not just the square root graph, but also the reverse, or the reflected version of that as well. So let's find out what happens when we go the other way. This one is the square root graph, and we want to find the inverse. And so, again, we're going to flip. And again, we're going to solve for y. And then we'll look at the graphs of these things. So if we flip our x and y, we're going to end up with x equals the square root of y minus 3 plus 4. Remember, this is not the inverse. You actually have to isolate y. Otherwise, yeah, you don't have the inverse. You don't have a function that's been solved for the output. So let's go ahead and solve. First thing I'm noticing is that I have that 4 that's just hanging out there. Let's move him. X minus 4 equals the square root of y minus 3. Okay, so to get that y alone, we're going to have to get him out of the root. So we're going to have to undo the root, and undoing the root would be squaring. So I'm going to square both sides. So we're going to end up with x plus 4 squared equals y minus 3. And then there's only one thing left to do. We just go ahead and add 3 to both sides. So we're going to end up with saying, okay, well, the inverse is equal to x minus 4 squared plus 3. Hooray! Now stop for a minute, and I want you to think about those two graphs. We're going to run into trouble again, aren't we? The first graph, the original one that we were given, was shifted over 3 and up 4. And then it followed your basic square root stuff. Now we're going to find the reflection over that line. And we did it. We did it algebraically, and we found this parabola. So let's go ahead and sketch the graph of the parabola. That is going to be a parabola that's been shifted over 4 and up 3, and there's my parabola. Shoot. Do you see the problem? I had half, and now I have both halves. So what we are going to have to do in this case is something really important called a domain restriction. A domain restriction restricts the domain, or the x's that you use to make your graph. And in our case, if you look at the graph, we only want this half right there. We only want all of the x's that are 4 and bigger. So for our inverse, we also have to include something that says, don't do this half of the graph. Only do the other half. Only do the part where it's bigger than 4 or equal to 4. So when we do an inverse of a square root and go to a squared, we need to remember a domain restriction. And so what we are going to do is our domain restriction is we want all the x's that are greater than or equal to 4. Or if you like interval notation, you could say 4 to infinity. That's your domain restriction. And one thing that's important to note is that this is for when you're taking a square root and you're going to a squared graph, because you're taking half a graph and you need to just have half a graph when you're left over. This doesn't happen all the time. It doesn't matter in a lot of odd functions, but this is important for when you're dealing with even powers. So now that we're all significantly confused about all the domain restrictions and the plus or minuses, let's look at another case. Let's take a break from those for a minute. If you look at this one, we have a cubic graph. That's raised to the third power, which means it is an odd power. So when we find the inverse here, we're not going to have to worry about all those little extra things. And let's see why. We're going to start out by flipping x and y. And then we're going to solve for y, just like we did before. So when we flip x and y, we're going to end up with x equals y minus 3 cubed plus 4. Remember, you're not actually done. You actually have to get y by itself. So again, well, what do I not want? That 4. So now we get x minus 4 equals y minus 3 cubed. Now you got to undo cubing. So to do that, we're going to take the cube root. That means we got to take the cube root of the other side too. So we're going to end up with the cube root of x minus 4 equals x minus 3. We can go ahead and add 3 to both sides so that our final inverse is the cube root of x minus 4 plus 3. And if you want, I don't know if you remember from the power functions, you could say that this was x minus 4 to the 1/3 power plus 3. They are the exact same thing, just depends on what you like writing. Now, let's think about the graphs of these two things and see if we need anything extra, like those fun domain restrictions and stuff. Our original problem was a cubic that had been shifted over 3 and up 4. And our inverse is going to be a reflection over this line, and our inverse gives me a cubic graph. So I look at my cubic graph, it's been shifted over 4 and up 3. Remember, a cubic graph has both parts, but it's sort of lying on its side. Oh, see how cool that inverse is? You can see the reflection, and it works out perfectly. I don't have too much graph or too little graph. So for this odd power, I actually don't need anything extra, and I am totally done. I found my inverse. So here is our lovely cube root. we're going to find the inverse of it. Now, think to yourself, if you're a savvy little learner, what do you suppose our inverse function is going to be? If we have a cube root, we're going to probably end up with a cubic. So, it's kind of cool. You're going to start noticing patterns, and inverses are really not bad once you get the hang of them. You flip x and y, you solve for y. Alright, in this case, I don't have anything to move, so I can go ahead and start cubing things right away. Cube that side to undo the root, so I gotta cube that side. So we're going to know x cubed equals y plus 2. One last thing to do is to deal with the 2. And we can say our inverse function is x cubed minus 2. Since I'm dealing with an odd power, I don't have to worry about any extra domain restrictions or plus or minuses, and I can say that I'm totally done. If you wanted to think about it graphically, and I do because I like to, we could see that our original function was that cube root that had been shifted over 2, and our new function is a cubic that's been shifted down 2. And how cool is that? You can already kind of see the reflection that had been happening over the line y equals x. So let's find the inverse of y equals x squared minus 6. This is a quadratic, so if we think about our inverse, we know we're going to end up with the inverse of a to raise to the second power, which is going to be the square root, or the 1/2 power. So we're going to start out by flipping x and y. And then we're going to solve for y. So we're going to have x equals y squared minus 6, and we're going to go, okay, I remember I have to get y by itself before I do anything else. So we're going to add 6 to both sides. X plus 6 equals y squared. Now we're going to take the square root of both sides. So we can say that our inverse function is the square root of x plus 6. Those of you who recall a couple slides ago know that we need something extra on this one. And again, I'm going to sketch the graph to remind you what that extra thing is. The original graph was a parabola that had been shifted down 6. My new graph is a square root that's been shifted to the left 6. 1, 2, 3, 4, 5, 6. Yes, I did it. I need the other half of the graph, right? I need this bottom half too. So this is a case where you need a plus or minus. So this was a plus or minus case. Because we needed the other half of the graph. We only ended up with half of it when we algebraically found the inverse. But nothing else that we did was wrong. We just needed to remember that extra step. Remember the plus or minus. So let's find the inverse of y equals the square root of x plus 1. We're going to start this one out, like all of our other ones, by flipping x and y and solving for x. Sorry, solving for y. Oh, that was terrible of me. Now remember, we're taking a square root, and so when we find the inverse, we're going to have to undo that root, and we're going to be raising something to the second power. So we're going to end up with a quadratic. This is one of those other special cases. So let's just do our flipping, and let's solve and see where we need to remember anything extra. Flip x and y, and start to isolate y. At this point, all I need to do is do some squaring. So I'm going to square both sides. And then I have my y all by itself. So the inverse of y is x minus 1 all squared. And again, let's think about the graph. Square root of x plus 1. Shifted up 1. There's my square root graph. And when we think about our inverse, shifted to the right one, and it's a whole giant parabola. Oh, drat. But we don't want this half of the parabola. We only want the right half of the parabola because that's what is actually the reflection. So we have to remember in this case that we need a domain restriction. that means we need to stop the graph. We need to say, hey, don't include that second half of the graph. So for this one, we can see that our domain restriction is going to start there at 1, and we want everything over to the right. So our domain restriction, we're going to say only include the x's that are bigger than or equal to 1, or in interval notation, 1 to infinity. One thing you can probably notice is that you can use the what's left inside the parentheses to help determine your domain restriction. And if you pause and rewind a little bit, you'll see that that was the same case in our other example as well. I thought we should end our inverse examples on a nice easy note. It's a linear, no extra things to worry about. We're just going to be finding the opposite of a line. We're going to flip x and y. And then we're going to solve for y. So we're going to end up with x equals 4y minus 8. Got to add 8. So we get x plus 8 equals 4y. And we're going to have to divide by 4. And then we'll have our inverse. So the inverse is x plus 8 divided by 4. Now you'll notice I like to check my answers by graphing them, and I can't really graph that. So I'm going to split up that divided by 4. I'm going to divide each term by 4. So we're going to end up with the inverse is actually 1/4 x plus 2. I like that much better because that's slope-intercept form and I can graph it. And we can see that if we graph our original function had a y-intercept down there at -8, and then it was pretty steep. It went up 4 over 1, up 4 over 1. That was our original graph. Now our new graph is y-intercept of 2, and it goes up 1 over 4, so it's a little bit flatter. But you can totally see that reflection over that line, y equals x. So the inverse of y equals 4x minus 8 is the line y equals 1/4 x plus 2. Now, math is always about proving things. Like, you might say that x equals 5, but how do you know x equals 5? And we know it because we used mathematical techniques that are already proven to actually show why. All those different adding 5 to both sides, that's all part of a proof. Now you can prove things are inverses as well. So the way that we prove things are inverses is actually use our composition of functions. If we have f of g of x and we have g of f of x, and they're both equal to each other and they both equal x, what we have are inverses. That means that g and f are inverses. And if you think about it, that makes complete and total sense. I'm undoing one of them with the other, and since they're opposites of them, all you're going to end up with is x. You're going to take x, do some stuff to it, undo some stuff to it, and have x again. So let's see an example of how we can prove an inverse. Let's use those two that we just did on the other slide. We ended up with, let's let the first one be f. Let's say f of x was 4x minus 8. And we ended up with g of x, or our other function, our inverse, was 1/4 x plus 2. And I want to prove that they're inverses. So I need to show this by composition. So we remember our composition. If we had f of g of x, what that's asking us to do is take g of x and put it inside of f. So here's our f function. It's 4x minus 8. But we're not using x this time. Remember, we're replacing it with g. So I'm going to put 1/4 x plus 2 inside that. Now we just need to distribute and combine like terms. So there we go. We end up with x plus 8 minus 8, which equals x. So haha, we verified this halfway. We're on our way to proving that they're inverses, but sometimes functions work one way and they don't work the other way. So we also need to do the second step of verification, which is g of f of x. And in this case, we're going to take the g function and we're going to input f inside of it. So the g function was 1/4 x plus 2. We're going to put f, the f function, inside of it. And the f function was 4x minus 8. Now again, it's just a matter of using those basic algebra skills. We're going to distribute. We're going to end up with x minus 2 plus 2, which is x. Hooray! This means that we have verified that f and g are in fact inverses, which is a good thing for us because these are what we found when we algebraically found the inverse, and if we had found something different and it didn't work, yeah, we would have done something wrong. So hooray for us, right? We just verified that we actually found inverses. And this verification is important. You can't just find the inverse and say, oh, see, I swear they're inverses because I found it. No, you could have done something wrong. You must show, if something asks you to prove or verify, that's the other word, I'm going to write it over here, verify. If you have to prove or verify that they're inverses, you need to use this composition rule. More often than not, you're just going to be asked to find an inverse, but every once in a while you might have to prove yourself, and here's how you can go about doing it. So, as I've started doing, I like to end on a recap, so let's remind ourselves about inverses. Inverses are reflections over the line y equals x. And we can find inverses on a graph or on a table by just flipping or switching x and y. And conveniently enough, that's how we do it algebraically as well, but of course algebraically we need to solve for y. Remember that cool notation we use, we write y inverse equals, and that shows that it's the inverse and it's not just some other function with a y in it. And when we're finding our inverses, we want to also remember that little trick for when we have even powers. So if we had a parabola and we went to a square root, we're going a whole graph to half a graph. So what we need to remember is that we need to remember our plus or minus sign because we need to include a whole graph and then another whole graph. And remember that when you're taking a square root or another even root, you're going to quadratic, x squared, or another even power, you have to remember your domain restriction because you're taking half a graph, mapping it to a whole graph. You have to cut that graph in half. You don't want a whole graph. So those are just a couple things to keep in mind as you're algebraically solving. And remember that to verify or prove things are inverses, verify, I spelled that right. You use compositions. So to prove things are inverses, you have to show that the composition one way is the same as the composition the other way, and it also equals x. Those are just the things that you need to remember as you are finding inverses of functions, whether using graphs, tables, or algebraically.